Okay, I made some adjustments. First of all, I think most of you, or all of you, already have returned the first exercise. Yeah, right. However, you still have time if you are not sure of everything yet until the end of this week to make some changes in your file. Don't change the link, just edit the document. I will be checking, say, maybe tomorrow or day after your stuff. I'll go through the stuff today already, but I start assessment on later on. And those who hasn't yet returned the exercise still have the end to the end of this intensive week, meaning Thursday is the last day. Okay, and then good news about today's exercise. You have 1 week. So it will be actually the following week. Next week, no, well, to the end of next week, which practically means Monday 12th morning would be deadline for that. And the next one, again, 1 week more. So this is heavy topic. Right. It takes some time to understand it, since you have basically also you have to do more work, since you are also translating it first from Japanese or English, and the Japanese translation is done, and then my notes are also in English, and then you have to produce English in your. So this is a double effort. Okay, so I understand it, and therefore we have this basically. The deadlines, for example, for the last exercise will be 5 weeks. So you have about 1 week to finish all of those exercises. I think it's fair, right? Do you think it's fair? Good idea. Is it good idea or not? Good. Great idea. Yeah. Okay. And that also takes some of the timely pressure off the studying. I remember myself as a student, and sometimes you need to press things to get things done. But okay, it doesn't need to be when it doesn't need to be. So when needed, you should be able to stretch yourself. But this course is not about stretching. This is about learning how to do practical digital signal processing, problem solving. It's not a stretch out practice. Okay, so now let's go to the lab tutorial. And by the way, I have already uploaded the lecture of this morning's lecture if you want to watch it at some point. Yeah, and yesterday's lectures and the lab tutorial are already there as videos. And after this lab tutorial, there will be another video here. Okay, yesterday I didn't say it, but anyways, I also downloaded the command history file. Okay, so there's all the commands what I did yesterday are on that file. There. Good. So, systems and lab. So basically what we are talking about here is the following exercise, which is the template is again there. You know what to do with that one. This exercise is about system fundamentals. How to basically first test what kind of system are we dealing with. So we are revisiting 4 of those 5 fundamental properties we just leave out the stability. The stability is basically tested easiest way using the zeros and poles. So I will show you how to test a system linearity, time shift invariance, and if the system is what causal. Sorry, sometimes my mind's okay. So so there are basically 4 different systems defined by these equations, and your task is basically to test each system on the first one for the linearity, and then for causality, and then for time shift invariance. Let's start from that one, but let's before starting go through the rest of those. So basically, those were the basic properties of any system. This 4th question and beyond, they are all linear time invariant systems. That system is defined by a block diagram, which has a d is the same as a z minus 1. So there's a delays, couple of here, couple of there, and your task is to find out what is the output for this system. What is the difference equation for this system? Just by following the block diagram, writing down basically what each one of those blocks does, and then it's quite simple operation. This is simple second order system, direct form kind of second order system. So it's quite straightforward to find out the difference equation for that. And the next one is basically how to define these system parameters B and A for the system. And there a most common mistake is the sign error on A. Okay, now you have been warned. And then number 6 is calculate zeros and poles and plot them on Argand's diagram. Then forward, then we change a system to another one, A and B for this system, yn equals, and then just write in the commands. And then calculate zeros and poles. Okay, so there are two different systems. One is defined by the block diagram, and then you define based on that one, define the difference equation and the transfer function, calculate zeros and poles. And then another system is defined by difference equation, and then you just need to do the zeros and poles and figure out if the system is stable. Okay, and the 9th, again, you need to work out a sound sample. Now the random noise has a noise amplitude, not the signal to noise ratio. Signal to noise ratio, but just the amplitude of the noise. So, and then basically a simple, this is the sound sample, and then you just run it. I have the, oh, okay. I have only 250 samples there. That's why, but it's a sound sample, but only 250 samples. It's 10 milliseconds long. Strange. Well, whatever. Then the last one is actually to have a system implementation. I will show you how to do it. So you use this signal sample, what you generated, run it through the system, and just observe by eyeballing, meaning just looking at it, comparing these plots, what did happen to the signal. Okay, and write your own observation. Anyhow, let's start from the first one. So how to test if a system is linear? For that one, I would need maybe to start my Octave. Why didn't do that earlier? Well, it wasn't that slow. All right. By the way, when you are in Octave, you probably want to also change your working directory to something else than the default. That's one way of doing it. If you need to do some adjustments on the default values when the system starts up, you can always also edit the Octave RC file. Have you checked the Octave how to basically make your own settings for the Octave when it starts up? There's a file actually. I'll just show it to you quickly. Octave RC, which consists of commands which are run before you get the prompt screen. There. Good. So if you need to do some permanent changes in the system, you just include those commands into your Octave RC file. Okay. So all right. So what we should do to test the linearity? So the linearity actually means that we are having the superposition is valid, meaning that if you have a system with a function f and you put two random signals in with two different any scaling variables, it should be the same as that scaling variable times the signal 1 in plus scaling variable times the other signal in. The next test is brute force test, and it's not really proving anything. It just gives you indication if it's a linear or not. Mathematicians say you need infinite time to run this test to prove anything. They are right, correct, that's absolutely right. But engineering, it's not exact science. There's always room for error. That's the natural science part of engineering. So in natural sciences, as in physics, there's always the error margin. Same here. Okay. Anyways, first we need to define the function. I will give you the example. So let's test if, say, f of x equals let's see if sine 2 pi x is linear or not. I know it's not, but let's see if the test actually tells you that this is actually a nonlinear system. So 2 pi x. And so this one is now that sine 2 pi x here. The test signals. Okay. The theory actually says, okay, for any input signals x1 and x2, we can use random numbers. They are as good as any. So these are actually random vectors. And these here are any scalar numbers, meaning, well, any is same as random numbers. Okay, let's define those. So we have A equals rand n1. So yeah, you'll get a random number. If you do exactly the same as I do here, you get probably exactly the same random number. That's because of the seed number for the random number generator is always starting on the same place. There is also a way to really randomize. This is semi-random number. Okay, if you want to randomize, you run the randomized generator. But anyways, this is good as any. And then we need another scalar number, rand n1. Okay, I'll suppress the printing. So this is another scaling factor for the test. And then we have the x1. Let me take, for example, 1 by 100. Okay. This would be 100 points long test vector of random numbers. Random numbers, and that this is also for testing purposes. You can make it bigger, you can make it smaller. Bigger you make, better this test is, but on the other hand, you don't need that many numbers on this case. Okay. Rand n, and then you need another test vector, and the only rule here is because you are doing this plus, you can multiply any vector with a scalar, that's fine. But if you are adding vectors, they must be the same length. The dimensions must match. So this is our another test vector. Vector. So next we calculate first the left-hand side and then the right-hand side and compare if they are the same. So, for example, LL equals, so this is the left-hand side equation. We have sine 2 times pi times, okay, AA times x1 plus BB times x2. Okay, so this is the left-hand side of the equation. There, and it's again, it's vector. Next, we calculate the right-hand side of the vector, of its equation. RR equals, you take A out, A times sine 2 times pi times x1 plus B times sine of 2 times pi times x2. There. So this is the right side of equation. And there we have L, L, and R, R, and you can already see on here that they are not the same, but anyways, these are vectors. How to test if the vectors are the same? You calculate the difference, second norm of the vectors. So basically a distance of these vectors. It's multidimensional, but it still means the same. You calculate the distance of the vectors. And that's done by saying, okay, now I have to check something here. Was it diff here? Help diff. Okay, maybe we'll try. So calculate the difference of. Hey, wait a minute. No. This is not the one. No. Well, at least you can get it by. Let's see. Help. Not distance. Norm. Okay. Let's calculate the norm of two vectors. So it's left-hand side minus right-hand side. If they are the same, this should be 0. Let's see. Not 0. So system is not linear. Okay, so that's the easiest way of testing the linearity. One small, caveat it actually has. Sometimes, because of the calculation inaccuracy, the answer will be very close to 0, but it's not 0. In case you get the norm which is very close to, say, or smaller than 10 to minus 12 or something like that, then it's usually due to the fact that you have a computing inaccuracy. So that means you still have a linear system. Let's see, do I have a good example? Yeah. Okay. Let's see. Another thing what is also good to remember is that to make sure that you are really calculating the function values here. If you have a simple sine 2 pi x, that's great, but sometimes you may actually have a say system that is a little bit more complex. Then you basically want to make a one single function that returns the value of your original function. And I will give you there an example. Are you familiar of how to make functions in Octave? Have you made your own functions in Octave? No. Well, it's easy. Would you like to see how it's done? Good. Okay. So first we start editing a file. So edit, and for example, this would be TKP fun. Yes. So put your own initial at the beginning and then just, for example, fun or something like that. Or in the exercise, you probably would like to name that exercise according to your accordingly. So if you edit, okay, create, it does not exist, we create it. Wow, this is really great. It actually gives me, this is new. So basically there is, so anything in between of this one actually will be, will be called when you call function by its file name. And function basically is always start with a function mnemonic, then the return val, meaning that okay, in those brackets it means it's optional return val, but if it returns, then it basically you call the function like that. Okay, you can also, if you know that there's only one input, I would actually go and just remove the extra input. Okay, since this function is always called like that one there, only one parameter. And yes, we always have the return value. The parenthesis is then obsolete. It does return the value. Okay, then for example, then we could have say the formula here, return value equals, let's make it easy, 2 times input. Was it input 1? Yes. A function that just returns 2 times the input. Yeah. Just save that, and after that we can call that function. So anti-kp fun at the value of 1 will return me 2. So it works. So now it's safe, actually could do the same test as in there. And I can, well, let's try that one. So then I can actually just call it the left-hand side and then do the right-hand side. Instead of those sign, I have the there, the left-hand side, right-hand side, and then calculate the norm. Answer is 0. This is a linear system. So if you have a system that just multiplies the input with the scalar number, then it's, that's quite obvious. Obvious result. Okay, so linear. All right, then a couple of tricks you need to also handle. So those tricks would go inside of this function what you make. And by the way, you can put whatever is needed inside of that function, of course. So it just returns what is the latest value of that red val there when everything is done. And the same way as in C programs, you can return also by saying return. So if you want to just cut the execution at some point, you just write return. And you can also use the return a red val here. There, it's similar to C. Okay. Anyhow, on some of these exercises, you actually need to know how to time shift data. The easiest way of doing the time shifting is to have a convolution of your data with the correct kind of sequence. And delay is easier to make as the advanced operation, because delay actually is the same as filter. Filter, and then tomorrow I will tell more about the filter, but in principle, filter is the implementation of your system. Now you can just take it as it is. So basically the delay is same as we would there. Zeros of how many, wait a minute, not one, n, how many delays you want there, and then at the end you have one. Then you have parameter one, and then you have the input. Okay, so that's the basic principle. You basically generate a delaying impulse response. So let's say, for example, 2 time step delay impulse response, D to I, would be 2 zeros at the beginning, giving it the 2 time steps, then 1, meaning that it otherwise returns the unity of the unity gain of the input, and that's it. So 2 time steps of nothing followed by unity. Meaning basically this filter with these parameters, it gives you convolution. If you convolve the data with that kind of impulse response, you will get just the delay part. Okay, let's try it. So we have this, let's see, stem our, let's see, for example, x1. It will take for a while. First time today I'm actually plotting anything, so it takes a little while. Come on! Stupid computer! There. So that's the X. Not a big deal. But how about this delayed X? Right. So X1 D to I is filter. Then the filter coefficients here are D to I and 1. Okay, you always have the 1 there. And then the input data, X1. So this is the delayed X1 by 2 data points. There. I will take probably another figure and stem that one. Okay, and compare. Let's compare. Well, boy. There we are. Are there any differences? So the lower figure is the original, and the upper figure is the delayed. And yes, actually, that, for example, that high peak is a little bit off. And I can see there are actually 2 zeros at the beginning. All right. So how come these are zeros? Of course, they are zeros. When you are calculating, it does not know where's the signal source. it has the random numbers as signal source, but when you are time delaying, you are introducing new numbers there. Those two values at the beginning are bogus values. They are filled with zeros. But still, we need to remember that those are bogus. Because, okay, they will actually cause some problems when you are comparing the differences of time delayed system outputs. Good. So keep that in your mind. So if you have this kind of delayed data there, you need to actually just not to take the whole data set, but a part of the data set when you are doing the testing. Okay. I'll just mark there. So the delay generates extra zero at the beginning. Explanation mark. There. Oh. All right. So let's see, since I have this nice system here, let me do something like this. Wait a minute, where is it? So, for example, in here, I could actually mark, just a moment. Okay. Yes. Which? Oh, one. Okay. This filter is actually implementation of IIR system. That one there corresponds to the parameters, system coefficients for output. So that's one because A0 is equal to 1 on the difference equation. Okay, you will understand it better tomorrow or after. But anyways, for the filter, you basically here have the same coefficients as your difference equation. These are B values and these are A values. So we have now a system with an impulse response of that one. And that's the coefficient for the coefficient A0 on the difference equation. So that's why. So let me mark them here. So that's hope this is not permanent. Yes, it is. It looked different. Yeah, that looked different. Would someone actually throw this one far away from here? Somewhere on those tables. Oh no. Hero will be mad at me. All right. So when we have this transfer function, you have some bk z2 minus k, ak z2 minus k. Actually, then you have a system which has the yn equals to sum of bk z2, not see. I should slow down. Bk times x n minus k minus ak y n minus k. All right, so here the a0 is always 1 because you are calculating it like that, and this index goes from n like that 1, and this is k from 0 to n. So this system, what I have there now, has the bk or b vector is 0, 0, 0, 1, and the a vector is basically, this is the first term, 1, but the others are 0. Okay, so practically this is a system which gives 2 time step delay. So 0 times x of n, 0 times x of n minus 1, 1 times x of n minus 2. Okay, excellent timing. Didn't see what happened here. Good. So now I have a system that actually returns a, well, now it returns a 2 times that time delay. But anyways, same 2-step time delay as a function in here. Now I could test if that system is linear. And you know it is linear. It's just time step. It's just a time shift operation, and that's also linear operator if you look at it anyways in a mathematical way. But in this brute force approach, if I then calculate the left-hand side, again, I just change the function. Whoops. Wait a minute. Oh, yeah. I don't need that one. I will just put the red valve there. No, some. Yeah. Now it's a little bit better. Sorry, the first one actually, I had the typo there. So anyways, this just returns the 2 time step delayed input values. And if I calculate left hand side, and then I calculate the right hand side, do I get actually, there is a chance that this is still linear. Well, it's still linear. But remember, we introduced also a couple of new elements there. Let me think. Does it actually? Yeah. It can happen that this comes up. Norm is different from 0 because of those points. What you then need to do is actually just to check the graphics. Are they really linear or not? One way of doing is to stem plot that norm. So not norm, but LL minus RR. This should be exactly 0 vector. Yes, that's a 0 vector. Good. While I had this function, okay, let's test. That's about everything on the linearity test. So you basically just calculate left-hand side and right-hand side separately. Next point would be how to test if the system is causal. Causality actually means that the system does not react before there's any input. So if the input is 0 for all n less than 0, then the implication is that f at x0 of xn is also 0 for all n less than 0. Okay, meaning practically if you have input which starts input which basically starts at time 0, so that you have zeros here and then any numbers here, and you run through the system that signal. What comes out should also have zeros here. It does not matter whatever. This can be whatever. Any numbers will do. Doesn't matter as long as this must be 0. So our test is actually if that the beginning part of the signal remains 0. And there basically our test vector, a perfect test vector would be where you have basically the index n and some random number starting from that point, meaning what we practiced yesterday. You start a signal at point 0, meaning the step function. All right. Causality. Tested for causality. And we already have almost a correct test vector. But let's generate the test vectors again. So let's put nn equals to from minus 50 to 50. So this is 50 index points. Sorry, 101 index points. Half of them on the negative and half of them on the positive side. Okay, good. So next we can generate the unit step function, which is simply double of nn is greater than or equal to 0. That's unit step function. And next we will generate that test vector. I call it xx equals, no, not double equal, but equals to uu dot times rand n size xx. So we will generate one random number for each, not xx, sorry, uu, for each index values, and then multiply with the step. And it looks like this. Look correct. Yeah, we can test the system with that. We'll just run this test vector through your system and see what is the output. And especially what is the output at the beginning on these values. And that's quite simple. First, let's run it through the system. For example, that my function, anti-KP function there. So we have the output. Y sounds like a good output name. Anti-KP fun. And input is the XX. So system output for input equals XX. All right, we can actually stem it and just eyeball. It seems that the those values are 0, but I don't believe it since they can be, say, 0.01 and still can't see it. So what we can do is actually calculate the norm of those values which have index less than 0. So calculate the norm of the output for those values which has index n less than 0. So I'm selecting logically index values less than 0 from this table and then calculate the norm of it. One line, lots of things happening there. Where index is less than 0. And that's 0. Excellent. Causal system. Okay. Well, yeah, the exercise is a little bit hard since there is another operation what you need there. I already almost kind of sort of say that we wouldn't need it, but it's the time reverse operation. I need to check if it actually was the swap or no. Reverse. Reverse in 7. By the way, the easiest way of getting some help on this octave is to Google it. Rearranging matrices, how to inverse matrix, and okay, inverse. Flip. That was easy. Flip. We will flip it. I will flip it. Okay. So basically, if you want to have a operator that does time advance. So that was easy there for on the linearity. I also already showed how to make the delay operation. But if you want to advance operation, what you would do, you would first flip the data, then you would delay it, and then you flip it again. So flipping meaning you are changing the direction of time. So when you are flipping back, that delay of that flip data becomes advanced operation of the flip data. Okay, so I will show you just that one in here. So we still need that filter, but we will actually first f input 1 flipped input 1 would be flip input 1. Okay, and then if you then let's do that one. It's Control C there, and say this is double flip. That this is the delayed flipped input. Okay, now this actually is the delay on flipped data, and then basically flip it back, so it would be double flipped input. Flip the F input 1. So after this one is the original time direction, but flipped delay, which is advanced. So this is 2 time step advance. And then calculate FF input. There. Wait a minute. Did I do it twice? Yeah. Sorry. I don't do any delays after that. So basically that's the return value already. So now this function actually returns 2 time step advanced signal. And now basically let's first see what it looks like. Got it? Did you get this? So it's first flip of the input, and then using that same filter to time shift this not input but finput. Okay, sorry. And then the return value is then basically flipped that one. All right. Ha. So that's how you generate time advance. But the same way as earlier, we got these 2 extra points of zeros on the left-hand side on the delay. Now we are actually flipping it first, so we are getting 2 extra zeros at the end. Okay, so if I just stem this there. Oh, wait a minute. That's not correct. So I have one flip too little here. Huh? What? I'm flipping the input. Delay in field flip data. Why it's still remains? Ah, that wasn't correct. See, I should just get the shifted input, not the flipped input. So let's see. Flip XX. There's something that I might actually not understand here, so let me try it like that. If I double flip that one, it works. Flip once, flip twice. So does anyone see the problem here? I didn't save it. Okay, remember when you are doing the editing of the functions, there's that save button there. Click it once in a while. All right, so now basically the stem that should okay. Now it looks a little bit better. So right, all right. So now this one returns the correct kind of value, and let's see, stem NNXX. So how about the indexing? Oh, right. We had the time advance operation, and you know that in principle this one should be non-causal system, since the output goes on before the input arrives. So how is our test now working in here? Test was to calculate the norm of y. Okay, I need to also calculate the values before that one. That's still 0, but I didn't calculate the y values. Okay. And then the norm, this should actually be, yeah, non-zero. So those two first values of the data sequence are on the negative index side. So no, so this norm actually shows that there is non-zero terms on the negative indexes, non-causal system. Okay, so that was about the causality. So we have a linearity test, causality test, and then we just need a time shift invariance test. Wow. Oh, all right. All right. So time shift invariance. Basically, it means that the system behaves today independent of the time, or as actually using block diagrams would clarify it a little bit better. So this is our system we want to test. And then we have the time delay. All right. Think of the same signal going to that system or the same signal going into this system. You have output here, you have output there. Are they the same? So time shift invariance actually means that it doesn't matter where do you put this time shift, the output should still be the same. So you can then chase this block to here. On the block design, it's very important to know if this subsystem is time shift invariant. Otherwise, you cannot move time delay anyways. All right, so basically what we are doing in time shift invariance test is test if delayed output equals to output of delayed input. Yeah, so that's delayed input, and that's for output for it, and that's the delayed output. Okay. So we have a test. Let's check, for example, our first system, and there. Although again, mathematics says you need to do infinitely long time to do the test, but this is a brute force. We just, test the system with with enough of random numbers, and then we can basically be quite sure if the system is time shift invariant or not. Mathematical proofing is again different from this engineering proofing. This is kind of just testing. Does it look like it is? Good. Let's move on. And then you end up having those nasty little features that actually appear only once in 1,000 years. But they're still there. But it's part of engineering. Okay, some, uncertainty is allowed. So we have the test vector, for example. Oh, well, let me just make another test vector. So, we will use x1. It's as good as any. So that's a random numbers. So we have the x1 as input. Then basically, first we run the system, the signal through my system and time shift, and now I just need to define what would be my favorite time shift. I will just use time shift of 1. And yes, 1 is good enough. So how do I do? Okay. So the output of y of time shifted function, output 1, y1, that's our output 1 for the system was anti-KP fun, and input is the x1, and then we time shift this one. And let's time shift with just 1 data point. Since this probably will be as good test as any, since if it's time shift invariant system, it tolerates any time shift. If it's not, it will fail also the time shift of 1. All right, so that's the time shifted output. And then the second one, y2, we calculate the time shift for the input and put it through the system. So anti-KP fun as a function of time shifted input. 0, 1, 1, x1. Okay. Output for time shifted input. And then we test if those are the same. And this test will fail. I'll show you. And you probably will understand it already why. Why those are different. I will be stemming the y1 and let's see, not n then. Oh, okay. y1 and then another figure for stem y2. 2 different figures. They look actually exactly the same, except for the except 2 points. This one is different, and that one is different, because I artificially introduce new numbers to my data. Those are the zeros are added when you are doing shifting of the data in the function. So to make sure this does not happen, you don't calculate this norm for the full data set, but take 1 point on each end out of the data. Basically, make sure that you are not artificially shifting this data, but Okay, so basically you will calculate the norm. Oops. I hate when that happens. Norm of y1 from point 2 to, what is the y? Let's see, for example, like this length. y1 minus, y1 minus 1, okay, like that, minus y2 from point 2 to length y2 minus 1. I'm still wondering if this is still enough. Well, we'll see. Did I put extra parentheses there? Maybe. Okay, I'll calculate first the norm, the difference. dy is equals y1 minus y2, and then just take the norm of, for example, df. Y1 size is, what is the size of y1? Okay, 80. What? Those are just arbitrary numbers. I'm just preventing of getting any artifacts from the either of the ends. Not df, dy. There, finally I got it. so basically, this one tells me that besides of those artifacts that I made myself, the rest of the data, the rest of those vectors are the same. Okay. So those were the tests for linearity, causality, and time shift invariance. Wow, that took so long. Okay, the next step is to have a short coffee break. Agree? Short coffee break, 15 minutes. Yeah. Then we'll, yeah.